Okay. All right. We're going to talk about pH, pKa, and the Henderson Hasselbach equation. Got this. All right. I'm gonna wing it. Hope I zone in, catch my zone. I had a hard time getting in my zone lately with these videos. It's frustrating. Okay. Okay. Let's look at this. We're going to start with the basic Henderson-Hasselbach equation. All right. What we are assigned to do is understand the relationship between pH and pKa at different points in a process. So if we are looking at our equilibrium curve, standard equilibrium curve, right here we know is our halfway point. And we know that at the halfway point, A equals B, right? Where our acid moles is equal to our conjugate base. Okay, so what that means, as we already know, is that pH equals pKa, right? We've talked about that because concentration of B over A equals 1, and the log of 1 equals 0, so the pH equals pKa, right? So in addition to that, if we are prior to the halfway point, right, we know that we have more acid present. The acid is in greater concentration than the conjugate base. And beyond the halfway point, we have more base than acid, right? Or the acid is less than the base, to try to keep that consistent, right? We are all in reference to A. Okay, well, when the acid is less than the base, the pH will be greater than the pKa. And when did I say greater than when the acid is less than the base? And when the acid is greater than the base, the conjugate base, then we have a pH that is less than the pKa. Now, for some reason, guys, that used to confuse me. Don't. If we are before the equivalence point, our pH is less, right? This is the pH at the equivalence point. We're not there yet. It's less than, right? If we were past, I think I said equivalence point, I mean halfway point. If we were past the halfway point, then you see that our pH is now greater than the Ka, which is equal to the pH at the halfway point. Okay. Essentially, if B is bigger than A, then this goes up. And if A is smaller than or bigger than B, then this goes down. All right, let's look at some particulate level diagrams and then we'll finish this. And we are going to make sure that we could draw particulate level diagrams for the different parts of the titration curve. You would want to be able to draw them. You would want to be able to determine if they were correct. If provided to you, you'd want to be able to like assess them or create them yourselves or look at them and say at what point in the curve are we in terms of conjugate acids and bases and hydrogens and hydroxides. So before the titration begins, well, what would we have? And we're going to have HA titrated with OH, all right? So we've got our weak acid. Well, before the titration begins, we'll just have some HAs, right? Now yours would probably be balls and colors, but so you'd have to look at what is what, all right? All right, so now the titration has begun, but we are now before the halfway point. So what should my new box look like? I want you to think about that, right? What should be in here? Well, I know that I'll have less of this, and I'll now have some of this, right? So I'm not going to include the water, but I did have 4 molecules of acid. Now 1 has been neutralized. At the halfway point, right, so we could have seen that last one kind of as, right, we had 4, let's label this A, label this A. We had 4, 0, 0, 0, right? That was our first graph or particulate level diagram. If we call this B, what we had was 4, 1, 0, 0. We lost 1, right? We lost 1, we gained 1, we gained 1. So that is what is referenced here. Well, at that point, right, we had 3, 0, 1, and 1. So it's essentially your ice chart, right? But in a visual diagram, it ensures that you understand the concept, right? Well, in our next part, where we are at the halfway point, right, we'll call this C, and we've got our reaction up there, right? I'm going to rewrite it. We know that at the halfway point, we originally had 4. We added 2, 0, 0. That's your I, C, E. We reacted half of it, and we now have equal amounts of conjugate acid and conjugate base. So I should have 2 acids, and I should have 2 bases. And they are equal, and we know that pH equals pKa, right? Up here, we know that the pH is less than the pKa, right? The concentration of HA is greater than the concentration of A, right? Here we have them equal. The concentration of HA is equal to the concentration of A. Now we'll be past the halfway point. All right, so continue some of our coloring. C references this, right? And then past the halfway point, and we'll call this D. I'm not sure what color is still available to me. I need some new colors, guys. All right, D. And hopefully you can envision where we would be, okay? Hopefully you could do this on your own, but this is our lesson, so Ms. Murphy's doing it for you. Right, we had to, now we're past the halfway, right? So -3, -3, +3, +3, 1, 0, 3, 3. So we see that now we've got more conjugate, than acid, we see that our pH will be greater than our pKa, and then our HA is less than our conjugate base. Notice if we were to keep going, what would happen? Let's do at equivalence point. Okay, this one's tricky. HA plus OH negative yields A negative plus HOH, right? So this is 4, 4, 0, 0, minus 4, minus 4, plus 4, 0, 0, plus 4, sorry, just doesn't matter. 0, 0, 4, 4. However, this is not the way this would remain. The A would then participate in equilibrium with the water, making HA plus OH, right? This is 4. We're not concerned with this. We have none, we have none. We have minus X, plus X, plus X, 4 minus X, X, X. So we see that we would, in fact, have some HA. We could kind of look at it like that. Right? And because of that, we see that we are slightly basic at the equivalence point. And the more of this that we continue to add, right, the more in excess it becomes and the greater increase in pH that occurs. Now, if you are thinking about this, you may ask yourself, well, Ms. Murphy, isn't that a weak acid? And wouldn't that then change the pH as well? And I would like to say yes. And you can go through all of the calculations, and I've done it. And what you will find is that once you have an excess of hydroxide, once you are past that equivalence point, it is the hydroxide that dominates the pH. So you can account for the dissociation of the weak acid and the OH, and the dissociation of the weak acid doesn't affect anything near to the, it's negligible as compared to the effect of the OH on the pH, okay? All right, guys, I think we did pretty good there. Right on. Yes. So